Okay, so this next session will be about cartography and spatial analysis. And our first speaker is Hadrien, and he's going to present us a talk called R and Space. So, your turn, Hadrien.
Thank you. If I speak loud, it's okay for you? Or, yeah, okay. So I'm assistant professor at the University of Paris. I work in the lab in quantitative geography. And I come here with two things, so with a story and an example of kind of studies we make in our lab. So the story. So it's my story. How to achieve a PhD in transport geography. Mainly you need three tools or methods: statistics and data analysis, spatial analysis, cartography, and network analysis. In 2009, you have this situation, you have to choose between of software and those here. So when I began my PhD, I was working with Windows operational system, and so there were two computer scientists in the lab, and they told me that I should maybe change my system and work with Linux. And if you do that, you know that you have to consider the change of the software ecosystem. And if you work with Linux, you can't work with SAS or with ArcGIS or with many other softwares. So here is the dilemma: SAS versus R. In 2009, I think R was already a better option, so it was not really a problem or a dilemma. But here there is a real dilemma. You have here ArcGIS, which was a very good piece of software in 2009. And here you have Quantum GIS, which was not a very good piece of software at that time. And also I was trained with this one, Miramont. It's Spanish software implemented at the University of Barcelona. So here I had really a big problem with that. I couldn't shift with Linux because I had to use ArcGIS. So here is here is the dilemma with the network analysis software. So this is the Wayback Machine. You can see the website of Quantum GIS in 2009. The version 1.0. It was bad. It was a bad option. And then this is the R project website. So SAS versus R, it's okay. I can choose R without any problem. And then I considered the option of using R for everything, and it was possible for everything, including the GIS and cartography tasks. So this is my story, and then until 2010 I used R as nearly the only language or software for my work, because it could I could do everything with it: the statistics, the spatial analysis, the cartography, and the network analysis. So this is the story, and then here is an example of the kind of study we make in our lab. So here you can see a map of the US Census Bureau. This is one of the most segregated cities in the US, Milwaukee. Here you can see as the dots black people, and here white people. So it's not really white, it's the typical category white, non-Hispanic, because if you are Hispanic, you're not white. And here you have many methods to assess the level of segregation in this city. So the first one is very, very famous and very old, and it has many names. Hoover or Schutz or Robin Hood or dissimilarity or Duncan index. And so it is a very simple difference between the distribution of the specific population of interest. So here, this is the population of black people in every zone in the city. And here is the sum, the total black people population. And here you have the rest of the population. So basically, it's the difference between the distribution of the population of interest and the distribution of the general population. And you can interpret this index as the proportion, for example, the proportion of black people that would have to be redistributed to get a uniform distribution. The problem with the Duncan index is that it is not really a spatial index. In fact, it is a non-spatial index, and you cannot use that index to distinguish between these configurations because you are measuring only the concentration between the zones and not the adjacency of the zones. So you need spatial autocorrelation indexes, and here is maybe the most famous spatial autocorrelation index. So here you have a difference to the mean for ego. Ego is the one spatial unit, and the neighborhood. So if you look at this formula, you can see that this index, the value of this index, mainly it is the covariance of the two variables, the variable for ego and the variable for the neighbors. And so this value is the same value as the slope of this regression line between ego value and the value in the defined neighborhood. If you have that slope, you will say that, for example, if ego has a very high percentage of black people, then the neighborhood has a very high percentage of black people. And if there is a little percentage, then in the neighborhood also. So this is a positive autocorrelation. The classical question is there, what groups are the most segregated in the residential space? Because you are using mainly census data, and so the census data tells you if the groups at home. But we had in a recent research project a relatively new question, which was what groups are the most segregated during the day. And here the question is, if you consider the daily mobility of people, you can ask this question: is the daytime population, the population during the day, more mixed or more segregated than the nighttime population? So I will answer these questions. To answer this question, we implemented a platform, the Mobiliscope, and here you can see in the Paris region the variation during the day. Here you have a timeline, and you can see the variation of the different groups during the day. Here, for example, if you select this place, so this is the 8th arrondissement, you can see the daytime population during the day. So here you have a very little population here, maybe 40,000 people at night, and nearly 200,000 people during the day. And you can see here all the categories. Here it is a socio-professional status. All the categories are increasing in this zone. And here you have the two indexes I was talking about, the Duncan index. You have a first answer to the question. So is the daytime population more mixed or more segregated than the nighttime residential segregation? So it is more mixed, which means that the daily mobility tends to mix the different groups. And here you can't see it, but it is the other index, so the autocorrelation index. So what do we need to build this application and to compute these indexes? First, you need a household travel survey, because you can't know with the census, you can't know where the people are during the day. So if you have a travel survey, you have something like this. For this individual, you have 3 trips from home to work by bus with a timestamp, from work to shopping purpose by bus, also with a timestamp, and then shopping, home, walking, with another timestamp. And with this table of trips, you can build a table of activities. And then you can associate with each activity a place, and then you can know where is this individual during the day. To do that, you have many ways to compute that. So I checked the old code I wrote, 9 or 10 years ago. So it was this package, and now I think there are more options. But you can do that with or without any problem. Then you have to compute the 2 indexes, and you have to compute them at each hour or at each minute of the day. For the Duncan index, the computation is trivial. You can do it even with paper and pen. But for the autocorrelation index, you will need a real spatial environment. So you will need a specific data structure for the spatial data. You will need spatial operators, in this case, in the spatial intersection. You will need snapping options and neighborhood and weighting policy to define the neighborhood of each spatial unit. And to do that, you have the SPDEP package, so the Spatial Dependence Package. It was released in 2002, and at that time there was only 1 or 2 contributors. So now there are 32 contributors to that package. And you can see the main description. So it's a collection of functions to create spatial weights, a spatial weights matrix from polygon contiguities. And of course, it is based on the SP package. I could do that with R, and in 2009 or 2010, it was really complicated to do that with any other software. So if you compute all these indexes at each hour of the day, then you will have to, you will produce a multivariate data set. And if you have that, you are, in geography, we are very used to build a classification of the different spaces. So here we can perform a factorial analysis, and then a classification, and here you have nine classes. Mainly, you have spatial units that are mixed during the day because there is a big, there are new populations. So this is the center of Paris. You have spatial units that are more mixed during the day because people are leaving the place, and you have places that are in an homogenization. because people are living. And this is typically the case in the peripheric zones where, for example, active people, mostly men, are leaving to work, mainly in the center of the region, and then the people who are staying in the place are mostly the poorest people and mainly women in that case, and so you have a more segregated situation because the zone is the population of the zone is decreasing today. So with R you can do that very easily and in the same workflow, as you may know. Then you can also build some new graphical proposal of new graphical devices. And here what you can see the evolution of the population and the evolution of the segregation during the day. So as the paper, the title of the paper was Social Segregation Around the Clock. So we wanted to propose graphics with clock shape. And here you can see, for example, this zone here. So it is the population is increasing during the day, and the segregation is decreasing. Showing here. And you can do that with ggplot. And I will finish with that. So this is a plot of the US Census report. Here you have the dissimilarity index, the Duncan index, in 1980, and here in 2000. And here you can see that there is a problem. So the Duncan index is in the two states. And if you look at the line here, you can see that mainly the slope. Here you have a line with a coefficient of 1, a slope of 1, and you can see that here the slope is the same. Mainly, if you compute a regression line here, the slope would be the same, but the intercept is a bit is negative. Here the problem is that the Duncan index cannot be compared because it depends mainly on two things. It depends on the proportion of the minority you are measuring, and it depends also on the population within the spatial units. So I think this is really a big mistake in the US Census report, and I don't know why they do that. But when you want to compare cities or compare different years, you have to, in a way, you have to standardize the index. And here is a method, a very old method. This is the paper, 1905. You can compute the dissimilarity index here, and then you can compute this index in a random distribution. And so you make a permutation, a stochastic simulation, and you compute lots of indexes with a random distribution, and then you can standardize this value with the mean and the standard deviation of your random distribution. With that, you can compare, for example, you can compare different cities. So here you can see the segregation during the day in 20 French cities, and here it is the segregation between men and women. You have very small cities with very small surveys, and so you can't say anything with the surveys, but the biggest cities are Bordeaux, Grenoble, Lyon, Toulouse. At night, the segregation of the two groups, men and women, is more homogeneous than a random distribution, and it's normal. So the sex ratio is constant at night. And then it is increasing during the day, meaning that men and women are moving in different places, And in some cases, and in Lyon, for example, you will see some places with a sex ratio of half women, half men during the night. But during the day, there are really some places full of men and places full of women, mainly because of their work. So yeah, and that's it. And I forgot the conclusion. So when I began my PhD thesis 10 years ago, I couldn't do that with any of the software pieces I was showing at the beginning. And I think it was impossible to do that for one person with one, I don't know, I would have needed more time, more people, more skills. And with R, everything is possible. I think it's a perfect conclusion.